Well, and now that we got that done, it looks like we can move on to a more exciting part of this video series. What I think I'd like to do now, if it's okay with you guys, is I would like to set up the foundations for AI. And I think it'll be a fun, interesting segment because I'm going to introduce to you a few concepts about how AI works. But before I do get to that, what I want to do is I want to set up the foundation for a debug system that will allow us to see what tile ID each tile is. So let's set up this foundation right now. And I like this screen. Let's set up this screen to be the one that we load into, since it was the last one we created. Cool. And let's go into the system.js file. We're going to go to where the debug system is drawing the red squares. You see that right here. Let's go into here, and what we're going to do is we are going to use the context to draw in the bottom right hand corner, or really any corner for that matter, of the entity what the ID is. So let's remember that when we begin to draw anything, we first want to set the begin path, or call the begin path function. And we want to, when we're specifically writing text or writing numbers, we need to set the fill style to the color. We can just use black. We'll set the font to 12 Arial. And then we can fill the text. So C fill text. And this method takes a few arguments. So the first one will be the actual string that you want to fill in. Now for us, we actually just want the ID of the entity. So let's see if we are using the ID up here somewhere. It doesn't look like we are. So why don't we just pull it out right here? And let me make sure this is still within the same for loop. Yes, it is. So we can actually just pull it out from that object. So const ID is equal to entity. And then where do you want it to go? So I've mentioned before previously that I probably would prefer it to be in the bottom right hand corner, although it can really go anywhere. So why don't we just, to start, we'll just use the X, Y values, and then we'll fill in the max width. So how large do we want this to be? Let's start with a nice round number like 50. We want to make it easily seen. Now that we have that all set up, let us do the stroke, which should write it to the screen. Let's turn this on now and see if it works. I'll press G, and it looks like it has 0 for link, but it has none of the other IDs for any of the other tiles are showing. Why is that? Well, let's see. Now, this is happening. So I think the reason why it's not showing for any of the other tiles is because the destination over is what's set for those tiles, whereas for link, it is source over. So when we get to debug, why don't we just do this? Why don't we add source over? Let's see if that changes anything. And it does. It changes everything, really. And the problem with this now is, so it looks good. However, I know that this 27, it doesn't belong to the top tile. It actually belongs to the tile below it. It's a little bit misleading. So as I mentioned before, let's just put it in the bottom left or right of the square. And let's start this again. Oh, I think I went in the wrong direction. I need to add 70. Oh, let's see now. There we go. So now I can see. So that's 11, 12, 13. It's still a little bit difficult to read. Why don't we make that bigger? Okay, that's a little bit more clear. Very good. And now that we got that done, we can begin creating our enemy. And the reason why I want to get this done first was because our enemy are, I can never pronounce the name, the Octorok or the Octotok, whatever this red enemy is called. I want him to be able to follow Link and pursue Link on the screen. And we're going to be using these tiles, the ones that are navigatable at least, for the Octorok. I'll call him the enemy, for the enemy to travel upon while he's chasing Link. And we're going to need to know each ID. And when we debug and go back and look at what's happening and why the algorithm we will write might not be working, we're going to want to know where the enemy is beginning at, which tile, and where Link is at. So now let's make the enemy. And I'm going to show you his sprite. It is in Overworld Enemies. And what I'm going to do is I'm going to render this guy right here, the red Octorok. If you know the pronunciation, please correct me in the comments down below. I'm probably slaughtering it. So I'll just be referring to him from now on as the enemy. So we'll be programming out his animation. So when he's moving down, he will have this column, the first column. When he's moving to the left, he will have the second column, so on and so forth. And to begin making our enemy, let's first set up his animation. And we can just go into our animation.js. I'm going to use the same kind of pattern that we made the Link animation with, because really it's going to be quite similar. Now, this enemy won't be able to attack per se. He's going to be doing damage to Link just by running into him. So we will be leaving the attack object empty for this enemy. But what I want to do is I'm going to just simply copy this. I'm going to close that. Let's go up and name this. We'll name him Red Octorok Animation. And let's go back to enemies. Cool. Let me do this. I'll leave this as an empty object. If you want to change it later, you can. Let's collapse. Get rid of the properties in this object. And now that we have that complete, we can actually kind of take a page right out of the book of Link, because these animations are actually at the same X and Y as Link was. So let's use these default values and see how this works. We can keep the number of frames to 2 and the frame speed rate at 3. We don't really need to change much, fortunately for us. So I think at the moment we just need to export this. And we should be finished in this file. Cool. Now that we have that, which is essentially the enemy's animation component, what we want to do next is we should go to our screen and insert the enemy into the screen object. Now, currently in the index.js file, we're not handling this in any way. We will be making changes to the index.js file to handle this information. What I'm going to do now is I'm going to actually add another property into screen E titled enemies. We can make it an array, and this array will have, or this array will be an array of objects. And this array is going to have, or this object in the array, rather, will have a few properties. The first two properties are going to be the X and Y position that we want the enemy to begin in. Now, let's see in the screen, maybe we want him to be coming from the top of the screen right here. We can select that spot, or we could put him in the middle. But why don't we just put him in the top? So we'll select the X to be 4, and I think the appropriate Y axis position would be 2. And there will be a third property that we could add. However, for this video, I don't think it'll be so important because I'm going to just be making this type of enemy. And that property would be some kind of property that denotes exactly what this enemy is. So it would, it could be a property that says enemy type string. And then another property, which we will get to a little bit later, is the item drop property. And this property is going to tell us what objects or what items the enemy will drop upon death. However, that will come a little bit later. And that will be an object as well. So now let's go to our index.js and allow for our index.js to interpret this array to create enemies where we want it to create enemies. And in our index.js, we need to go to the load screen function because that is where the magic happens for us. And since this is a property that's actually outside of the num rows property, or the screen property, I should say, we're not going to put it inside this for loop. What we're going to do is we're going to put it outside of the for loop. And we're going to create our enemies pretty much just like how we're creating our entities already in this loop. So let's just make an if statement. And with this if statement, we'll just make sure that there is a screen object. So if there is a screen object and there's a screen object dot enemies dot length that is greater than 0, then we'll enter into this logic structure. And what will we do in this logic structure? Well, as I just said, we will pretty much copy the pattern that we already set up here. So I'll use this as a example. Let's scroll down to here. So let's follow the pattern above. So we'll loop through the enemies. I is equal to 0. And let's pull out the enemies now. Screen object. Enemies dot length. We can just leave it like this. So let's, just like in this for loop, let's create a components array. This will hold all the components. And since it's an enemy, we are making a variety of assumptions about it. Now, in a more complex object, we could have things that would denote information about what type of components that it has, right? For this example, we're not going to make it too complicated. We're pretty much going to assume that every enemy has the same kind of, same components, right? It has a position. It has a sprite. In the future, it will also have a hitbox and it will have a health component. So these are assumptions that we're making, but keep in mind if you wanted to make a more complex version of that, you would be able to do that with this object right here. For us, let's create the dummy position component. And what will its values be? Well, we have the values right here. So why don't we pull out the const xy from the enemy, and also let me just get the enemy, enemies.i. Cool. And then we can just do x, y. And then as for the width and the height, we can simply just set that to, we could do tile size, but we can also just make it slightly smaller so it fits between the blocks well. And then we can components.push that right in. So that's one. The next thing that we're going to do is we need to have a sprite component. Well, as I mentioned, I'm just making this enemy. Now, later on, we could have an enemy type or some kind of property in this object in our screen.js file that would denote what type of enemy it is, where then we could have a, some kind of switch case that would then tell us or would direct our code to the correct block it should execute. Since we're just focusing on making one enemy, let's keep it simple, and we will just make it that red octarock value. Cool. So the path, we should set it to, well, let's take the enemies. Oh, there we go. Okay. It will be starting from assets, so it actually will be overworld, enemies, .enemies.png. Believe that should work. And then for the source rectangle, well, let's just take the very first sprite. Here we'll do y -2, -1, and we can set the width to something like 19, the height to 19 as well. That's fine. And then we will push that into the component as well. The components array. So now we have the components that the entity would need to be rendered. What else will our entity do? Well, it's going to move to be able to be interacted with by the movement system. It needs to also have a movement component. So let's code that out. That one is going to be simple. It's going to just movement component. It's going to just have default values of 0 for both properties. Let's push that into the components. Dummy movement component. And then the last but not least thing that we need to push into this array is the animation that we just created. So let me import that, save it. And then once this is done, let's use the registry to create this entity. So registry, do this registry, create entity components. Okay, I think that is good. Let me double check what is going on with the path and registry. I think that is good. Actually, you know what? No, we do need assets in front. World enemies.png. Cool. So I think that's good. Let's get this entity, console.log it out just to make sure that entity, everything is working as it should. Make sure you save your file. Okay. 187. Oh, and if you see in the corner of my screen, he's over here. Okay, so it is working. Okay, so we are properly creating the entity. X2, Y2, X4, Y2. Oh, interesting. I think what we need to do is we need to times this by tile size. because these are just the coefficients. They're not the actual position. There we go. Now he is where he should be. Awesome. He is facing up currently. I believe he should be facing down, but I think it's because we probably have up set. Yeah, up is set right here. Not that this matters too much, but to keep it consistent. As soon as he starts to move, that value will change, but let's just keep it consistent. I think it's the best way to go about it. But cool. Okay, so the enemy is being created. Fantastic. And to illustrate this, let's just add a value to the velocity just to show you guys that he is indeed moving. I'll add it to the VX. He's going to move over the bushes, but I just want to show you that he will turn. You see that? So he's going over the bushes. Don't worry about that at the moment because he won't actually ever come into contact with the bushes. Now if we go back, let's make the enemy animate between his two frames. So if we go into system, let's take a look at the animation system. Now currently, our enemy is not being animated, so let's take a look as to why that possibly is. Well, the enemy either needs to have this value set to true or this value set to true. Obviously, we are only handling is attacking A with a user input, right? That's if Link is swinging his sword, then we're animating. So it doesn't make sense to have the is attacking A applicable to the enemy because we're not really going to be having him attack. More so just running at Link. So what we could do is we could alter this should animate property. We're also handling should animate with the handle user input function in the index.js for Link. But maybe we could do this in a bit more intelligent way and have it applicable to all entities. Now the way that I'm thinking about is if the entity has any velocity at all, then he should be moving, right? We should be able to have him, we should be able to see him walking. So why don't we go up to our movement system and edit these values? So right here, we are currently dealing with the animation facing value. Why don't we also set it to should animate as well if the velocity is not equal to 0. So if either velocity is not equal to 0, so if either velocity has some kind of value, right, animation should animate should be true. Else, animation should animate is equal to false. And let's go into index.js and remove the older code that was making Link animate because we won't need that anymore. So I can just go here. Delete all these values. And we'll take a look. We see that the enemy is animating. And Link also animates as well. Very nice. And this finally brings us to one of the most interesting and also one of the most challenging parts of this video. We're going to be creating our very own artificial intelligence engine or architecture to allow our enemy to switch between states while in the game based on the enemy's own internal state. And this state will be derived from events that come from the outside. For the specific behavior we're going to be programming out first, the external information will be Link's position on the map relative to its own position. The pattern that I'm going to introduce to you is something called state-driven agent design. It allows developers to make the AI give off the impression that it's actually thinking and making decisions based off what happens in its environment. We will be programming out a very simple pattern, but it's not very difficult to extend once you learn how to build this pattern out. So let me pull up an example that I found on the internet to better illustrate what exactly this looks like. And then I'm going to show a very simple model of what we will be programming out. So if we go to the browser, I'm using a website called draw.io to illustrate this. So let me zoom in and I'm going to show you this example I found on the internet. So while looking at this diagram, let me explain to you the simulation or the scenario that this diagram was made according to. So in this simulation, we have a room, right? Imagine a big room and it has many obstacles in it. And inside this room, there is a cat and there are 3 mice that are wandering around. Now, think about the cat. It's wandering around, and while it's wandering around, it is looking for a mouse to chase. But until it sees one, it continues to wander around the room. And as soon as it sees the mouse, it will increase its speed and chase the mouse until the mouse has either been 1, caught, or 2, it can no longer see the mouse. If the mouse, on the other hand, sees the cat, or it realizes it's being chased, it will attempt to run away from the cat. It'll either hide behind an obstacle that the cat cannot get around or get under, or it'll just run as fast as it can away from the cat. Now, if the cat ends up catching the mouse, it'll just take a few minutes to kill it, and then it'll go back to what it was doing before, wandering around the room. But on the other hand, again, if the cat loses sight of the mouse, it will run to the last known position that the mouse was at to look for the mouse. Okay, so if it sees the mouse, it will start to chase it, but if it reaches the last known position without seeing the mouse, it'll just go back to wandering around the room. Okay, this is state-driven design, and the cat has at least 4 different states. Now, if you can see here, it has the cat wander state, the chase mouse state, the seek mouse state, as well as the kill mouse state. While the mouse, it just has 2 states. It has the mouse wander state and the evade cat state. As you can tell, each state is represented by a box, and the arrow represents a transition away from the state to the next state. So this is effectively 2 artificial intelligence that are interacting with one another. In a more complex game, we would be building out something like this where the AI, might do something based on what the other AI is doing. For example, in Halo 3, one of my favorite games of all time, if you kill one of the grunts' leaders, the rest of the grunts will run away in fear. If you ever played that game, you know what I'm talking about. They react to one of their allies being killed, and then they run away, right? Those are states. So they must have a fighting state and a running away state. They may have a wandering around state, which I'm sure that they do. So these are all the states that AIs can have. Now, something that story does not have is the difference between types of states. There are normal states, which are, if you want to think about it, they're lesser priority states. And then there are something called global states or higher priority states. So for example, your current state right now while watching this video is learning to program video games. However, your global state or your higher state might be your hunger, because once you get too hungry, it will force you to cancel the learning how to program state in order to engage in a behavior that satisfies the requirements of your hunger state. Does that make sense? So I'm going to scroll up, and this is something I just wrote out. And if I zoom out, you can see we're going to craft 2 states for our AI. The first one is the search state, which will be our global state. And the second one will be, and I should change the name of this, will be we could say our hunt state, where the AI is running at Link because it wants to hurt him. Now, our global state for our AI is that it's always going to be looking for Link. So this will be the thing that takes priority. if the AI loses track of Link for whatever reason, the AI will then look for him again. We'll also make our entity have this state every few seconds because once the Link moves, the AI will need to search for him again. So we'll continually call the state on an interval. This state, the hunting state, will be the thing that the AI is doing when it's not participating in its global state. And there's something I want to make clear, and I wrote it down right next to the state, and I said, when you think of states, you should not think about data. States in this manner, they're not exactly data, but it's actually the behavior of the function that the entity is in the middle of performing. So the states won't be having data that defines themselves, but rather they will be the behavior. It will be the behavior of the state that defines it. So hunting, that's a behavior. There's no data that's associated with hunting necessarily, no properties. There will be exceptions to this rule, but for the most part, all the data that is needed to go between states will be kept inside components. The state itself contains the logic that creates the behavior and mediates between them. And this logic will be split up into 3 separate functions. There will be logic that's fired upon entrance into the state. There will be logic that is fired when the state is executed. And there will be logic that is fired when the state is exited. So if we take the chase mouse example, it might look like something where once the cat sees the mouse and it enters the chase mouse state, the enter function could fire logic that says something like turn up velocity to 10 because now it's running. And the execute function could be something like navigate obstacles because the mouse might be weaving between chairs and desks and tables. The cat might need to move side to side, run around things. And the exit logic may be something like once the cat catches the mouse, if that is what happens, the cat will eat the mouse and then go back to wandering. And in that part of the state, the exit logic that mediates between the states will go back to cat wander, right? So we went from cat wander to chase mouse to kill mouse to cat wander again. Okay, so how are we going to write this or organize this in our code? So currently we are using an ECS design architecture pattern for our video game. Where does it fit in there? So what we're going to do is we're going to create an object or a class really called the state machine. And each entity is going to have a state machine. And similar to how the registry controls the system, the entities, the components, and their relationships, the state machine is going to be that kind of facilitator for the states. So it's going to be the thing that is in charge of 1, holding the states, 2, executing the logic, and 3, exiting and entering states. So as I wrote right here, every entity will have its own state machine, and the state machine is an object that keeps track of the previous state of the entity's global states and current state. It will keep data as well as setter functions that will set the state and an update function which will call the execute function of the state. I hope that was clear. I know I'm saying the word state a lot. It may be hard to follow, but as we write this code, I'm sure it'll become a little bit more clear, or at least I hope so. Let's go to our code and code out a practical example to get you used to this idea and the application of it. So we can close these. And what I'm going to do now is let's create a whole new folder. We can just call this folder AI. In this, I want to create 2 files, the state machine.js file and the Octorok states.js file. And we just need these two open. So the octorock states file is going to have multiple classes defined in them, and we're going to instantiate these classes after we define them. While the state machine will only have one class, and we will define the methods within the state machine to facilitate changes between the states, as well as containing the information, some of the properties that we need to properly execute and facilitate changes between states. So let me start with the state machine. Let's export it just now. We can set this as the default. Okay. Constructor. So there's going to be currently 5 properties, and I'm going to add an extra one that we will delete in a little bit because where we will have a more sophisticated way of handling the specific thing I'm putting it in for. But these 5 properties are going to be, well, the first one will be the owner of the state machine. So this state machine is going to belong to a specific entity. So we can pass it in like this, and we'll set the owner to owner. Now the next 4 are states that can start as undefined, and they are 2 of each. So there is a global state and there is a current state. And to just think about it simply, lower priority, higher priority. I know the word global is misleading because it makes you think everyone has access to it. However, I've read books on this topic, and this is how they refer to it. They call it the global state. On more complex builds, it is accessible. Some entities sometimes have access to other entity states and things of that nature. We won't get into that. But just know that global just really means higher priority, okay? So we have 2 states right here. And then the other thing that we want, and we won't be taking advantage really of this, but I want to teach you the proper pattern. I want to teach you this theory properly and the design that goes along with it. So we're going to have a previous global and this previous current. Because sometimes, and you actually saw it in that cat example, sometimes the state will revert to a prior state if something occurs. Like I think in the last example, the cat was no longer seeing the mouse, so he had to revert to the previous location that he was at, or something like that. Those are times when you need to have a list of the previous states. And it's actually very common for enemies in video games to do something like that, where they lose track of the player and then they go back to like wandering around. It's very often seen, especially in older video games. Cool. And now that we have this, I don't want to continue building out this class without first showing you what the state is going to look like. Now, I'm going to make a very simple state, and it's going to just be move right. We won't be using this class. I want you to go through this with me as a way to get comfortable with it. The move right state, and let me actually just write state next to it so it's clear, will not have any data associated with it, so we can keep this constructor blank. It will have 3 functions, as I mentioned before. It will have an enter, an execute, and an exit function. Make these arrow functions. The 3 E's. Okay. And on enter, what I have in mind of doing is to just simply show you the transition between states. What I would like to do is just take link's position and make a change of where the enemy is based on link's position. Now, this won't be the final way we do this, but it's a good exercise for you to understand how the state can change based on external variables or external information. So it's going to take two things. The move right state is going to take its owner, and it is going to take the player. Okay? And what's going to happen is we're going to do a logic check in here. So if we're going to be comparing the position, right? So actually, let's just get the position components from the owner and the player. So position out of owner.components, then player position, from player.components. Cool. So if, and actually we can even pull this out further. I prefer to do that. Let's get the X is owner X, Y owner Y with you know what? I don't even think we need that. Let's just get the X's. Owner position const X player X. So if the owner X position is to the left, so if it's less than, right? If it's less than px, let's then get the movement component and let's move him to the right. Vx, and we'll set it to 1. Okay? And in that, and with that, that's pretty much it. Now we can duplicate this class to make it simple. We'll call this the move left state. And now we'll flip that. We'll make him move to the left. We now need some kind of intermediate state or the global state where the enemy is able to facilitate a change between the moving right and the moving left state. Let me add this S in here as well. Let's just add a class search state. And just like the other classes, it will have a enter execute, and exit function. And in the execute function, we will include some logic to determine what state we need to move or what state we need to go in, right? The move right state or the move left state. So again, it's a little similar. So we can actually take what we did down here and copy and paste it. And in here, we can do change state to one thing, else change to another. So here is where the state machine is going to come into play. And I'm going to actually put the owner in here as well as the player. So the state machine is going to have a method that will change the state. And when it changes the state, it will make sure that it fires off the enter and the execute functions. So let's do change state inside the state machine class. And if we need new state, because we're going to be passing a new state in. So if there is a current state already, that means we're replacing the current state with a new one. we must set the previous current to the this current state, and then set the current state to the new state. As well, we're going to add, oh wait, before I forget, and then we must do this current state exit in here, and then at this current state enter. And I know right now none of our states have enter or exit functions. We will not really be using them in this video series. I've mostly, and I said this before, but I do want to hammer this home that I'm following the design pattern because in more complex AI systems, there will be data and behaviors that you will want to initialize before you do the execute block. And then there will be things that you would like to clean up using the exit block. So there is some boilerplate code I'm just making you learn right now. However, I'm doing it for your benefit so you can extend this later on and use this in whatever you decide to do in the future, and you can use it to its fullest extent. Anyway, if you go to update, or if you go into the state machine, we will have an update function, and that update function will call, if there is a current state, it will call the this current state execute. And if there is a global state, which we do not have one of those yet, don't worry, we will get there. This global state execute. Okay. Actually, I'm going to change this all to undefined. Then within this owner, so the owner will have state machine change state to, so it'll change state to move right, change state to move left. Okay. And down here we will initialize each one. So const search state, new search state, const move right state, const move left state is equal to new move left state. Okay. And with that, move right state. Let me make these lowercase and follow the camel case pattern. Cool. And then, so now that we have this completed, let's go into our index.js and let's put this into our animate. Or actually, before we do that, let's go into our entity class and let's add this state machine is equal to state machine. Now the player won't have it, but the enemy will, and it's okay if the player's state machine is undefined. That's fine. That won't really bother us. And in this entity, let me call it enemy. Odd. It's already defined. Okay, entity. That's fine. Entity state machine. You know what? It doesn't matter too much here. Currently, this entity is going to be instantiated with it undefined, and maybe that's better that way because I don't want to go into this code and add it to every single entity that exists. I only really need it for my enemies. To avoid writing complex logic where it really is just this simple, we can just use the dot accessor and just set it to new state machine like that. We'll pass the entity as itself because it's the owner. And the last thing I'm going to pass, and I'm going to add this into the state machine.js, we need to get the player in this example. And this is the property before I was referring to that we will not be doing this in the final implementation, but just for the sake of this example, I'm going to pass this player. I'm going to do that. I'm going to do player. And then we can pass the player in through here, this dot player, because it's that simple. Okay, player should be defined by that point as well. And then for the execute functions, we need to pass owner and player in here for the current state. Let's see. I don't believe I'm missing anything. Okay. Then last but not least, let us update, or let's call the update function for the state machine in update. So we can handle this in a variety of ways. We can just call it right in the update function instead of setting it on another interval. That sounds okay to me at the moment. Let's see how that works though. You can just put it down here and do let for I is equal to 0. Yes, actually, and here is the rub. We do not have access to enemies in the game. So we have a variety of options. We can push this entity into some kind of array, whether it's in the registry or the game class. I think it makes more logical sense to just put it into the registry. Even though we will be using it in the game class, it just seems to me like this is where all the entities live, and I kind of want to keep it consistent. Let's make a blank array, and we can do this registry dot enemies. We can just push it in like that, and then now when we do this loop, this registry dot enemies dot length increment I. Okay. And then const enemy, this registry enemies dot I, enemy state machine update, just like that. That looks good. And its current state, I don't believe we actually set the current state. It handles everything. Let's do entity state machine, change state, and we are doing the search state, I believe I called it, right? When we need to export these, search state, move left state, move right state. There we go, so they're all accessible, but search state right there, okay. Okay, and that looks pretty good. I think we have our starting state. I have not made the logic in here change it yet. So now that we have the change state function, we'll move right. Or actually, let's just use search state. That's what we should be doing, so we don't make an assumption. Let's delete this here. And that looks pretty good. Let me give it a once over. Oh, wait. Oh, I immediately see something wrong. We got to take this out. My bad. We got to put it into an else. Right there. And also change it here. Cool. Let's see what we have now. Oh, okay. Well, that looks like it's working. Let's just make sure. Okay, he's moving to the right until he's on the same column, and then he's stuck, which is fine because we were kind of expecting a similar behavior. And he's effectively moving. You can see that he's reacting to where Link is in relation to him on the y-axis. See? I can run past him. He's going to change direction. That looks good. So we're not obviously going to be using this again because he's just running through obstacles. That's not what we want. We're going to need to have a more complex implementation of the state machine, but this is the idea. This is the pattern we'll be using going forward. To finish up this state pattern, let's add up and down as well. And let's then alter the search state to work with those. So why don't we just copy the move right state and make the appropriate changes. So this time we don't really need X, we need Y for everything. Then move up state, move down state. Flip it. Flip the signs. And that looks good. Now let's alter the search state to handle the y-axes as well. So we can simply just create another logic structure, really. And it can be something as simple as copying this and essentially just doing, this would be move down if it's -1. Okay. So instead of the movement being -1, we do move down state, and this would be move up state. And how this code is currently written, once the enemy gets to Link, it's going to not really know what to do, and it's going to gyrate back and forth, and I can even show that to you now. Let me fix that. OY is not defined on 22. Yes, because we're not pulling that out, of course. So YOY, as well as for this one. YPY. Let's see now how we're doing with that. This current state enter is not a function at state machine 32. Machine 32. Scanner state enter. We did not initialize it. Move up state equals new move up state. Const move down state is equal to new move down state. And let's make them all camel case for the actual objects to keep it clear. Yes, that's why it would be throwing an error. Oop, there we go. Okay. I mean, it's currently going side to side, but we can see that it is going up and down. Okay, and it has some weird behavior. It's going too far to the right. Let's see what's going on. The up and down is understandable, though. Okay, so judging from that behavior, I have a feeling that there is an issue with, well, obviously with this block of code. What I think is happening first is we need to decide whether or not we are moving horizontally or vertically. Now, you can come up with some fancy algorithms to kind of randomize the decision between going horizontal or vertical first. We will simply just choose to go in the horizontal direction first. So if OX is equal to PX. Then we'll go in the Y direction. So if those two values are not equal to one another, the unit should always move left or right first. And or the enemy shall always move left or right first. Now let's see what we get with this. Okay, so what I think is happening now is that it's a little weird sometimes with translating the velocity to position, because sometimes you can end up where you're in between values, and that can create like some funky behavior. So for example, if let's just console.log out OX and PX so I can show you what I'm talking about. So as it gets to the same x-axis, we're seeing a lot of values. Okay, see, it goes from 499 OX to 501. It kind of bounces in between 501 and 409, and that's due to the velocity, the translation of the velocity into the position. What we can do, and this is often a technique used by many games, is that we can have something that handles, or we can have a logic structure that will be basically just do an approximation. So when it's close enough, the value will simply just be set to what it should be, or a value that can work. So it was bouncing in between two values. So what I want to do is I want to actually alter this logic structure and say if, and we're going to use an absolute value, if OX minus PX is less than or equal to 2, okay, we will just set the OX to the PX, and let's then let's set the movement to 0. So we're going to have to take movement, player movement, or sorry, owner movement, not the player, and let's just set the VX equal to 0 like that. Okay. So now what should happen is when it is either 2 or less, we'll just automatically set it to the owner's VX, or sorry, to the PX of the player. And that should fix the issues we have with it going left and right. Oh, cannot assign to a constant variable. Let's just change these to lets, because we will be doing the same thing with the Y as well. Watch it go. Cool. My game is a little laggy just because I'm also running a recording software that's taking a lot of energy and a lot of power. But cool, we see it's working. So, and then if it moves, if we move, a little funky behavior, but that's good enough at the moment. Let me set this up for Y as well and see what we get. So if math absolute XOY minus PY is less than or equal to 2, OY is equal to PY, and then owner movement VY is set to 0. Okay. Cool, and he stops at my place. Let's see. Sorry for the lag. But yeah, that looks pretty good at the moment. I have a bit of an issue. Let's do this. Because what's happening right there is that the velocity of Vy is affecting the entity when they're also moving to the right. So what I would like to do is if they're moving left or right, the owner should not have X or Y velocity. Sorry, if they're moving left or right, they should not have Y velocity. There we go. So Vy should be set to 0. For move right, Vy is equal to 0. And then that should also be the same for if they're moving up or down. So their Vx velocity should be set to 0 as well. Move down. Move up. Move right, Vx, 0. Move left, V, 0. Okay. Let's see, okay. Okay, that still works. Great. Cool, and now he follows me properly without that weird movement that it was doing before. Awesome. And so for the foundations of our AI system, that is pretty much it. Now, this is going to get a bit more complex, but congratulate yourself because you've learned the foundation, the building blocks for building AI for video games, for building enemy AI. It's a super cool skill, and I'm glad that you've stuck with this video this far. We will be expanding upon this in a little bit.